On April 18, 1955, world newspapers published news of the death of the great scientist. Newspapers published a photograph of Albert Einstein's desk with an open notebook in which he took notes and worked on the theory that would ultimately define his life, the unified field theory. This concept, also known as the theory of everything, is the search for a single equation that can unify all the forces of nature. That is, to combine gravity, electromagnetism, strong and weak nuclear interactions. Einstein's quest to find this equation was driven by his belief that understanding the fundamental principles that govern the universe would allow us, in his own words, to read the mind of God. 6 years earlier, 2 weeks after his 70th birthday, which he called a sad event, Einstein confessed in a letter to Maurice Solovin dated March 28, 1949. "You think that I look at my life's work with a feeling of complete satisfaction. Up close, everything looks different. There is not a single concept about which I would be confident that it will remain unshakable. I'm not even sure I'm on the right track. Contemporaries see me as a heretic and reactionary who, so to speak, has outlived his usefulness. All this, of course, is a matter of fashion and is explained by their frivolity, but a feeling of dissatisfaction rises within me from within." For decades, Einstein was unable to overcome the mathematical difficulties of creating a unified field theory. However, he certainly did not consider his work useless or meaningless. On the contrary, in a letter dated December 14, 1946 to Michel Kaku, with whom he shared his most intimate things, the scientist calls it fruitful and believes in the future. Hope also permeates his letter to Michel dated April 15, 1950, although Einstein is aware of the unimaginable complexity of the problem. From this it follows that the possibility of comparison with something known from experience should be expected only with a rigorous solution of a system of equations. Images are discovered in which reflect known from experience and their variable effects. But since this is monstrously difficult, one can understand the skeptical position of modern physicists. For now they have every right to consider my path fruitless. But it won't last long. Gradually they will see that it is impossible to understand the essence of things using a quasi-empirical method. What is the skeptical position of modern physicists? And how did the author of the theory of relativity and that very formula E=mc², which clearly explained the fundamental connection between mass and energy, become almost a dissident by the end of his life? If in the 1920s physicists followed Einstein's efforts to create a unified field theory with admiration and hope, then in the 1930s, against the backdrop of the impressive successes of quantum mechanics and quantum field theory, Einstein's authority noticeably declined. None of his attempts to derive specific equations of motion of elementary particles from the general scheme were successful. At the same time, quantum physics has proven to be amazingly effective. The year 1932 was especially rich in discoveries. This year, just 5 years after the completion of the Copenhagen interpretation of quantum mechanics, new elementary particles were discovered. The neutral neutron, which, along with the proton, is part of atomic nuclei, and the positively charged positron, the antiparticle of the electron, predicted by Paul Dirac. An interesting paradox of history. The honor of discoverer of antiparticles should have belonged to Albert Einstein, but he missed this opportunity, being too carried away by the search for a unified field theory. 3 years before Dirac, in the fall of 1925, Einstein published a short paper in the Dutch journal Physica entitled The Electron and the General Theory of Relativity. It begins with an unusual phrase for scientific articles. The following remarks are so simple that I do not hope to say anything new in them. From the point of view of today's understanding of physics, this phrase indicates that the author did not fully realize the genius of what he did. After all, we are talking, no less, about the discovery of antimatter. This example clearly demonstrates the complete focus on the theory of everything. Some of Einstein's contemporary scientists looked at his scientific efforts with pity, others allowed themselves mocking jokes. The colossal difficulty of the task did not discourage Einstein until the last days of his life. He struggled with mathematical problems, not sparing himself, just as Don Quixote struggled with windmills. It is not for nothing that Einstein himself recalls the hero of Cervantes's novel in that letter dated April 15, 1950, one of his last messages to Michel Besso. It is true that under such circumstances you find yourself in the position of Don Quixote, since there is no certainty about when it will be possible to find out whether a theory is true or not. But the longer the struggle for a unified field theory continued, the more often doubts came to mind. In one of the subsequent letters to a friend, they are expressed most clearly. All 50 years of conscious searches have not brought me any closer to answering the question, what are light quanta? Today, every fraudster thinks he knows this, but he is wrong. Now I am confident in the possibility of a natural generalization of the gravitational equations, but I cannot find out whether there is anything physically true in this. Erwin Schrödinger, Werner Heisenberg, Niels Bohr, Paul Dirac, Max Planck, Richard Feynman, Julian Schwinger, Abdus Salam, Steven Weinberg, Sheldon Glashow, Murray Gell-Mann, Stephen Hawking, Roger Penrose, John Archibald, Wheeler David, Gilbert Hermann, Wal Oscar, Klein Edward, Witten Bryan, Green Juan, Meldicena Michael Green, John Schwartz, Gerard T. Hooft, Carlo Rovelli, Lee Smolin, Kip Thorne. The list goes on and on. All these are the names of scientists who worked on the theory of everything. But is there any result? Did any of them manage to derive the God equation? Today, many leading physicists believe that we are finally closer to a solution. And perhaps the leading candidate for a theory of everything is string theory. She argues that the universe is not made of point particles, but of tiny vibrating strings, each node of which corresponds to an elementary particle. Within this theory, if we take a super-powerful microscope, we will see that elementary particles such as electrons, quarks, neutrinos are nothing more than vibrations of tiny threads, reminiscent of a stretched elastic band. If such a rubber band is pulled in different ways a sufficient number of times, then in the end we will get all the known elementary particles of the universe. This means that all laws of physics, without exception, can be reduced to the harmonies of such strings. Chemistry is melodies that can be played on strings. The universe is a symphony, and the thoughts of God, about which Einstein wrote so eloquently, are cosmic music resonating in space-time. Nobel Prize winner in physics David Gross wrote, "String theory is a piece of 21st century physics that accidentally fell into the 20th century." And here are the words of Kip Thorne. String theory is an amazing theoretical development that tries to unite all the forces of nature into a single coherent picture. It's a bold and beautiful idea that has captured the imagination of physicists around the world. In general, finding a strong candidate theory of everything, such as string theory, is not just an academic matter. Each time the discovery of new laws of physics changes the course of development of civilization and the fate of all mankind. Thus, Newton's laws of motion and gravity laid the foundation for the machine age and the Industrial Revolution. Michael Faraday and James Clerk Maxwell laid the foundations of the theories of electricity and magnetism that allowed us to light cities, create powerful electric motors and generators, and communications such as television and radio. Einstein's formula E equals mc squared explained where stars get their energy and helped harness the energy of the atom. The creators of quantum mechanics, Erwin Schrödinger and Werner Heisenberg, along with other physicists, laid the foundation for today's high-tech revolution with the help of quantum supercomputers, lasers, the internet, and the gadgets that surround us. Ultimately, all the wonders of modern technology are the result of the discoveries of scientists who studied the fundamental interactions of our world. And now science appears to be close to creating a theory that will unify all four forces of nature. But what questions can a theory of everything answer? Something like this. What happened before the Big Bang? Why did this explosion even happen? What is the nature of dark matter and dark energy? What's inside a black hole? Is time travel possible? Are there wormholes leading to other universes? How many universes are there, and what is their nature? Are there higher dimensions? And how to interpret the double-slit experiment and the quantum superposition of the electron? This video is dedicated to the search for the final theory and some events from one of the most amazing pages in the history of physics. We will remember the discoveries of the past that gave birth to the wonders of technology, from the Newtonian revolution and the study of electromagnetism, the understanding of relativity and quantum mechanics, to modern string theory and a number of other theories that will make it possible. Take a fresh look at the structure of reality. Physicists and mathematicians are searching for one elegant equation that can cover everything from the smallest subatomic particles to the greatest cosmic structures. But love and interest in science can be expressed in simpler and more practical ways. For example, read books by Michio Kaku. He is one of the most famous theoretical physicists and co-founder of one of the branches of string theory called string field theory. This video was inspired by his book The God Equation, The Search for a Unified Theory. If you want to truly enjoy satisfying your curiosity and gaining structural knowledge, read or listen to this book. And then, my attempt to fit the history of physics into 70 minutes so as to reveal the main topic of the video, the theory of everything. In search of a theory of everything, the ancient Greeks were among the first to try to bring order to the seemingly chaotic world around them. Philosophers such as Aristotle believed that everything could be reduced to a combination of the four primary elements: earth, air, fire, and water. However, it was difficult to explain the complexity of the world with just these four elements. The Greeks offered two different explanations for this issue. The first explanation came from the philosopher Democritus, who proposed that everything was made of tiny, invisible, and indestructible particles called atoms, meaning indivisible in Greek. Critics have argued that direct evidence of their existence is unattainable because atoms are too small to be observed directly. However, Democritus provided compelling circumstantial evidence, such as the gradual destruction of the golden ring, which suggested the presence of atoms even if they were invisible. Even today, much of our scientific understanding relies on indirect evidence. We obtain information about the composition of the sun, the complex structure of DNA, the age of the universe, and much more through indirect measurements, although we have never observed these phenomena directly. This distinction between direct and indirect evidence becomes crucial when discussing the proof of a unified field theory. The second approach to understanding the world was proposed by the mathematician Pythagoras. An insight came to Pythagoras, and he decided to apply a mathematical description to such an earthly phenomenon as music. Legend has it that he discovered a connection between the sound produced by the string of a lyre and the vibrations caused by striking a metal rod with a hammer. He realized that both generated musical frequencies within a certain range. This discovery suggested that something as aesthetic as music could be based on the mathematics of vibrations, indicating that different objects in the world could be controlled using the same mathematical principles. In other words, the entire variety of objects around us must obey mathematics. In the 17th century, there were scientists who dared to challenge prevailing ideas and explore the nature of the universe. Johannes Kepler, one of the first to use mathematics to understand the motions of the planets, served as an imperial advisor to Emperor Rudolf II and escaped persecution for incorporating religious elements into his work. Former monk Giordano Bruno was less fortunate. In 1600, he was found guilty of heresy and executed. His crime was to suggest that life could exist on planets orbiting other stars. Yes, a terrible crime. Galileo Galilei, often considered the father of experimental science, narrowly escaped a similar fate. Faced with the threat of death, he abandoned his theories. However, he left a legacy as a telescope, an invention that radically changed the scientific world. Through the telescope, one could see that the surface of the moon was covered with craters, that Venus went through phases corresponding to its movement around the sun, and Jupiter has its own satellites. All these were considered heretical ideas. Unfortunately, Galileo was placed under house arrest and banned from receiving visitors. He eventually became blind, possibly from looking at the sun through a telescope. Galileo died a broken man, but in the year of his death a child was born in England who continued the work of Galileo and Kepler, ultimately developing a unified theory of celestial mechanics. Isaac Newton is perhaps the most influential scientist in human history. In a world occupied with magic and witchcraft, he had the courage to develop the universal laws of celestial mechanics and to use newly invented mathematical methods known as integral and differential calculus to study natural phenomena. As physicist Steven Weinberg stated, it is with Isaac Newton that the modern dream of a definitive theory truly begins. At one point, Newton's theory was considered a theory of everything, capable of describing any movement. It all started when Newton was 23 years old. Cambridge University was closed due to the plague. One day in 1666, while walking on his estate, he saw an apple falling and asked himself a question that would change the course of human history. If the apple fell, would the moon also fall? In his notebook, he drew a fateful drawing. If you fire a cannon from the top of a mountain, the cannonball will travel some distance before hitting the ground. However, if you increase the speed of the core, it will fly further and travel around the world at sufficient speed. Newton concluded that the same natural law that governs the motion of apples and cannonballs, namely gravity, was responsible for the motion of the moon around the Earth. To describe this, Newton introduced the concept of forces. Objects move because they are pulled or pushed by forces that are universal, measurable, and can be described mathematically. Thus, Newton proposed the key concept of unification. In 1682, a significant event occurred that changed the course of history. A brilliant comet appeared in the sky, and everyone, from royals to commoners, was animatedly discussing the news related to it. Where does it come from? Where is the comet going? What does she portend? Edmund Halley, an astronomer, was particularly intrigued by this comet. He went to Cambridge to meet Isaac Newton. By that time, he had become famous for his theory of light. By passing a beam of sunlight through a glass prism, Newton demonstrated that white light was divided into all the colors of the rainbow. In addition, Newton invented a new type of telescope that used mirrors instead of lenses. After asking about the much-debated comet, Halley was amazed to learn that Newton could prove that comets move in elliptical orbits around the sun, and could even predict their trajectories using his theory of gravity. Moreover, Newton observed comets through a telescope of his own design, and their movements exactly corresponded to his predictions. Halley was amazed. He immediately understood the significance of this scientific breakthrough and offered to cover the costs of printing the work, which was destined to become one of the most important scientific publications, Mathematical Principles of Natural Philosophy, or simply Principles. As predicted, Halley's comet appeared over Europe on Christmas Day 1758, further enhancing the posthumous reputations of Newton and Halley. Newton's theory of motion and gravity is considered one of mankind's greatest intellectual achievements because it includes a single principle that unifies the known laws of motion. Even today, it is Newton's laws that allow NASA engineers to guide space probes across the vastness of the solar system. Over the centuries, numerous confirmations of Newton's laws have emerged, significantly influencing both science and society. In the 19th century, astronomers observed a peculiar anomaly in the sky. The position of the planet Uranus deviated significantly from predictions based on Newton's laws. Its orbit was not a perfect ellipse, but was slightly distorted. This suggested that either Newton's laws did not apply in this case, or there was another unknown planet influencing the orbit of Uranus with its gravitational attraction. Confidence in Newton's laws was so strong that physicists, including Urbain Le Verrier, began to calculate the estimated position of this mysterious planet. In 1846, astronomers discovered a planet in the predicted location with a deviation of just 1 degree and named it Neptune. Thus, Newton's laws provided the key to understanding the mysteries of planets and comets and laid the foundations of mechanics, allowing us today to build bridges, skyscrapers, engines, airplanes, trains, rockets, and space probes. Video of the catastrophic destruction of the Tacoma Bridge in Washington state in 1940. These are not just dry and boring equations. It is part of our understanding of the structure of reality that has had obvious consequences in changing the course of modern civilization, allowing us to create the wealth and prosperity that we see around us. Newton's laws, based on the unification of the physics of the sky with the physics of the earth, helped usher in the first great technological revolution. The mystery of electricity and magnetism, it took another 2 centuries for the next major breakthrough to occur, resulting from the study of electricity and magnetism. Even in ancient times, people knew that magnetism could be used. For example, the compass, invented by the Chinese, accelerated the onset of the Age of Discovery. However, electricity scared people, as it was believed that lightning was a manifestation of the wrath of the gods. Michael Faraday was the very person who laid the foundations of a new field of knowledge. They say that when he came to a party, he was always positive. Faraday demonstrated that moving a magnet inside a wire generated electricity inside the wire. That is, a moving electric field creates a magnetic field. Gradually, Faraday came to the conclusion that these phenomena represented 2 aspects of the same entity. This simple observation led to the age of electricity, when hydroelectric dams were built that could light entire cities. Faraday also introduced the concept of field, one of the most important ideas in physics. The field consists of lines of force that fill space. Magnetic lines surround each magnet, and the Earth's magnetic field radiates from the North Pole to the South Pole. Even Newton's theory of universal gravitation can be interpreted in terms of a field. The Earth revolves around the Sun because it is in its gravitational field. Faraday's discovery helped clarify the origin of the Earth's magnetic field. When the Earth rotates, its internal electrical charges also move. This constant movement within the Earth creates its magnetic field. Currently, all known natural interactions of the universe are described precisely in the language of fields, first introduced by Faraday. Maxwell's equations, however, the study of fields required Maxwell's equations, a new branch of mathematics, namely vector calculus, which was used by James Clerk Maxwell. Maxwell was an outstanding mathematician who made outstanding discoveries in physics. He realized that the behavior of electricity and magnetism described by Faraday and others could be generalized and expressed in precise mathematical language. But there was a strange thing. One law said that a moving magnetic field could create an electric field, and another law said the opposite. A moving electric field could create a magnetic field. How so? Maxwell came up with a brilliant idea. What if an alternating electric field creates a magnetic field, which in turn creates another electric field, which then creates another magnetic field, and so on? He suggested that the end result should be a traveling wave in which electric and magnetic fields constantly alternate. Using vector calculus methods, Maxwell calculated the speed of this traveling wave and obtained a value of 310,740 kilometers per second. The result amazed him. Within experimental error, the resulting speed was surprisingly close to the speed of light. Then he took another bold step and declared that this was the light itself. Light is an electromagnetic wave. Today, Maxwell's equations form the basis of television, lasers, electric motors, generators, and much more. Not only have they given us the ability to communicate almost instantly using radios, cell phones, and fiber optic cables, but they have also opened up the entire electromagnetic spectrum, of which visible light and radio waves are just two bands. In the 1660s, Newton demonstrated that white light could be divided into all the colors of the rainbow by passing it through a prism. In 1800, William Herschel asked himself a simple question: what is beyond the edges of the rainbow, whose colors change from red to purple? He took the prism he used to draw rainbows in his laboratory and placed the thermometer behind the red prism, where no color was visible at all. Suddenly, the temperature in this seemingly empty place began to rise. This meant that in addition to red, there was another color that was invisible to the human eye, but still contained energy. This is called infrared light. We now understand that there is a whole spectrum of electromagnetic radiation, most of which is invisible because each region has a specific wavelength. This means that the reality we see around us is only a tiny part of the full electromagnetic spectrum, a tiny element of a much larger universe of electromagnetic shades. Some animals see much more than we do. Bees are able to sense ultraviolet radiation, which is invisible to us, but important to bees because it helps them find and navigate the sun, even on a cloudy day. And because flowers acquired their gorgeous colors to attract pollinating insects such as bees, this means they often look even more attractive when viewed under ultraviolet light. And the peacock mantis has 12 types of photoreceptors that perceive the wavelength range from 300 to 720 nanometers. That is, he sees immediately in the optical, infrared, and ultraviolet ranges of the spectrum. Well, just some kind of predator. Combining Newton's and Maxwell's equations gave us a very convincing theory of everything, at least everything that was known at the time. At the turn of the 19th and 20th centuries, many scientists declared the end of science. It was a turbulent period when it was believed that everything that could be discovered had already been discovered. What physicists didn't know at the time was that the two pillars of science, Newton's equations and Maxwell's equations, were actually contradictory to each other, and one of them is destined to fall. And the key to the solution was in the hands of a 16-year-old teenager. This man was born in 1879, the year Maxwell died. Einstein. The quest for unification. As a teenager, Einstein posed the question that the quest for unification was destined to change the course of 20th century history. He asked himself, is it possible to outrun a beam of light? Many years later, he would write that this simple question became the key to his theory of relativity. Over the next decade, he persistently searched for an answer. Unfortunately, many perceived him as a failure. Despite his exceptional academic achievements, his professors did not approve of his reckless approach to life. Since he was already familiar with most of the material, he often skipped classes, which resulted in disapproving grades from professors. All of his job applications were rejected. At some point, wanting to support his common-law wife and child, he even thought about starting to sell insurance policies. Imagine this. You open the door and Einstein is there trying to sell you insurance. Unable to find a job, he felt like an outcast in his own family. In one of his letters, he gloomily wrote, "I am only a burden for my relatives. It would be better if I did not exist in the world at all." In the end, he managed to get a job as a third-class official in the patent office in Bern. In the silence of the patent office, Einstein was able to return to the question that had tormented him since childhood. It was there that he was destined to start a revolution that turned physics and the whole world upside down. Einstein wondered, what would happen to Maxwell's equations if an object moved at the speed of light? Interestingly, no one had asked this question before. Using Maxwell's theory, Einstein calculated the speed of a light beam relative to a moving object, such as a train. He expected that the speed of this light beam, observed by a stationary observer outside, would be equal to the sum of the ordinary speed of light and the speed of the train. Because, according to Newtonian mechanics, the velocities must add up. To Einstein's surprise, he discovered that the light beam continued to recede at the same speed. However, this seemed impossible. According to Newton, if you move fast enough, you can catch up with anything. Common sense suggests the same thing. Nevertheless, Maxwell's equations stated that it was impossible to catch up with light. This realization was a revelation for Einstein. Only one of them could be right, either Newton or Maxwell. But why can't we catch up with the light? Einstein's idea was that since the speed of light is measured by clocks and rulers and is constant no matter how fast you move, space and time must bend to ensure this constancy. This means that if you are in a fast-moving spacecraft, the clock inside the spacecraft runs slower than on Earth. The faster you move, the more time slows down, a phenomenon described by Einstein's special theory of relativity. Therefore, the answer to the question, "What time is it?" depends on your speed. If a spacecraft is moving close to the speed of light and we observe it from Earth through a telescope, everything inside the ship appears to be moving slowly. Moreover, everything inside the ship seems to shrink and become heavier than before. At the same time, the astronauts inside the ship believe that everything is in order. Einstein later stated, "I owe more to Maxwell than to anyone else." Today, such an experiment is not difficult to carry out. If you put an atomic clock on an airplane and compare it to a clock on Earth, you will see that it runs slower, a tiny fraction, a trillionth. But if space and time can change, then everything that can be measured must change, including matter and energy. The faster you move, the heavier you become. The source of this additional mass is the energy of motion. For example, you weigh 70 kilograms. This means that if you reach 90% the speed of light, you will weigh 160 kilograms. If 99%, then about 500 kilograms. And if you accelerate a little more, less than 1% to 99.99%, then your mass will already be 5 tons. The exact relationship between matter and energy is described by the formula E equals mc squared. This same equation answers one of the oldest questions in science. Why does the sun shine? The answer is quite simple. The sun glows because, as a result of the compression of hydrogen nuclei at very high temperatures, part of their mass is converted into energy. The key to understanding the universe is unification. For the theory of relativity, this is the unification of space and time, as well as matter and energy. But how is this achieved? The beauty of symmetry and beauty for poets and artists. Beauty is a fleeting aesthetic characteristic that evokes strong emotion and passion. For physicists, beauty lies in symmetry. Equations are considered beautiful when they have symmetry, that is, when rearranging or replacing components leaves the equation unchanged. It is invariant under this transformation. Likewise, the beauty of a snowflake is that its shape remains the same when rotated 60 degrees. The sphere has even greater symmetry. Rotate it around the center at any angle and in any direction, and it will not change. The body parts of some animals are arranged symmetrically around a central axis, such as the radial symmetry of starfish. Fractal symmetry occurs naturally in Romanesco broccoli because the same pattern is repeated at different scales. That is, each smaller piece of broccoli is a miniature version of the whole. There are also more interesting types of symmetry, such as scale symmetry in self-similar objects such as the Sierpinski triangle. It exhibits scale symmetry. The same shape appears at different scales, but the overall structure remains the same. The atomic structure of a crystal lattice exhibits inversion symmetry, in which the arrangement of atoms remains unchanged when inverted through a central point. I decided to give so many examples of symmetry here because it is understandable and even pleasant to us on the most intuitive and deep level. She is part of us. The human body has bilateral symmetry, meaning it can be divided into two equal halves along a central plane. This plane runs vertically from the head to the feet, dividing the body into left and right sides that are roughly mirror images of each other. Although the human body is not perfectly symmetrical, Many of its features and structures, both external and internal, exhibit symmetry. External bilateral symmetry is, for example, eyes, ears, arms, and legs. Within the human body, there is also symmetry in organs such as the lungs and kidneys. Physicists find an equation beautiful when its parts and elements can be interchanged without changing the result, that is, when there is symmetry between its components. Gravity is a curvature of space. Any physicist of the first half of the 20th century was clear that the theory of gravity as a curvature of space of universal gravitation by Newton and the theory of Einstein are incompatible. According to Einstein, if the sun suddenly disappeared, the Earth would feel its absence only after 8 minutes. Newton's famous formula for gravity does not contain the speed of light. Consequently, gravity spreads instantly, violating the laws of relativity, and the Earth should feel the absence of the sun immediately, instantly. Einstein spent 10 years describing the nature of light. He then spent the same amount of time studying gravity. The answer to the question, "What is gravity?" came to him at the moment when, leaning back in his chair, he almost fell. He realized that at the moment of the fall he felt weightless. Einstein recalled this as the most joyful idea of his life. If you imagine yourself in an elevator that suddenly breaks down and begins to fall, you will feel as if gravity does not exist because you and the floor of the elevator will fall at the same time. This correspondence between acceleration and gravity is called the equivalence principle. Many people think that astronauts in space are weightless because there is no gravity, but in fact the ISS and the astronauts on it fall to Earth the same way, creating the illusion of no gravity. In other words, acceleration in one frame of reference is identical to gravity in another, which is explained by the curvature of space. To clear things up, let's take a look at the solar system. We, being on Earth, feel gravity as a force pulling us towards the sun. However, an observer from the outside will not see any force. In his opinion, the space around the Earth is curved, and the void causes the Earth to revolve around the sun. This is very important to realize. It is not force that pushes planets, but space curved by mass that makes planets fall. Recently, I was lying in bed talking on GPT chat while studying English at the same time. We were discussing the solar system, and I was reminded of 2 ways Einstein tested his theory of relativity. The first is gravitational lensing. Simply put, it describes how light rays, which have no mass, should travel in a straight line. But when passing near massive objects, especially black holes, their trajectory is bent due to the deformation of the fabric of space. Einstein realized that at the moment of the eclipse of the sun by the moon, its mass would slightly bend space, and he was able to confirm this experimentally with calculations. The second example is the anomalous shift of the perihelion of Mercury. As a result, Einstein, having developed the special and general theories of relativity, decided at all costs to create a third, even more grandiose one. His goal was to combine all known interactions in the universe into one equation. Quantum sunrise in 1869, Mendeleev came up with the idea of systematizing the quantum sunrise of all chemical elements in a dream. When he woke up, he created a table of the elements, demonstrating their periodic properties. This table combined more than 60 known elements, but there were gaps in it. And thanks to the periodic table, he was able to predict the characteristics of the missing elements. But what caused the elements to group this way? What process or laws of nature underlie this order? In 1898, Marie and Pierre Curie discovered new unstable elements. One of them, radium, glowed without a visible source of energy, violating the principle of conservation of energy. This indicated the need for a new theory. Previously, scientists believed that chemical elements are unchanging and eternal. However, now in laboratories, scientists observed how some elements, such as radium, were transformed into others, emitting radiation in the process. Scientists have calculated the rate of decay, and it turns out that they decay over thousands and even billions of years. Curie's discovery shed light on a long-standing debate. Geologists studying the slow processes of rock formation have suggested that the Earth has existed for billions of years. However, Lord Kelvin, the famous physicist, suggested that the Earth cooled in just a few million years. Who was right? It turned out that geologists were closer to the truth. Lord Kelvin did not take into account nuclear forces. This process could have warmed the Earth's core over billions of years due to the decay of radioactive elements such as uranium and thorium. This nuclear interaction became the source of energy for earthquakes, volcanoes, and even continental drift. In 1910, Ernest Rutherford conducted an experiment by placing radium in a lead box with a small hole. From this hole came a thin beam of radiation, which he directed at the gold foil. It was expected that gold atoms would absorb this radiation. But, to his surprise, the radium radiation passed through the foil as if it were not there. This was an astonishing result. It meant that atoms were composed mostly of empty space. The quantum revolution in 1900, Max Planck, a German physicist, explored a simple question. Why do hot substances emit light? Blacksmiths have known for centuries that when objects are heated, their color changes from red to yellow to blue. But when physicists tried to calculate this effect, they ran into a problem. Newton argued that atoms vibrate faster when heated. And according to Maxwell, oscillating charges emit electromagnetic radiation in the form of light. At low frequencies, the combined model worked. But as the frequency increased, the light energy tended to infinity, which is absurd. Max Planck then proposed that energy was actually emitted in discrete packets, which he called quanta. He then discovered that he could accurately calculate the energy emitted by heated bodies. The hotter the object, the higher the frequency of its radiation. Therefore, today, for example, we know exactly the temperature of the sun, which is about 6,000 degrees Celsius. Following his research, Planck determined the magnitude of light packets of energy, known as quanta, and described them using a constant. If Planck's constant were equal to 0, then the equations of quantum theory would be reduced to Newton's classical equations. Simply put, all the strange behavior of elementary particles, such as quantum entanglement, superposition, quantum tunneling, can be easily converted into Newton's laws as we know them by setting Planck's constant to 0. This is why quantum phenomena are not so noticeable in everyday life. Our perception of the world is based on Newton's macro laws, since Planck's constant is a very, very small value that affects only the subatomic world. In 1905, Einstein applied quantum theory to light and showed that light is not just a wave, as Maxwell predicted, but also a particle, photon, as Planck predicted. It consists of photons, which are quanta. Each photon creates electric and magnetic fields around itself. They, like waves, obey Maxwell's equations. But if light exists in two forms, as a particle and as a wave, then doesn't the same strange duality inherent in the electron? The answer to this question was destined to shake not only the world of modern physics, but also civilization itself. Electron waves physicists have discovered to their surprise that electrons, previously introduced to us as ordinary particles, can also exhibit the properties of waves. I think you all know very well about the double-slit experiment, which explains the essence of the interference pattern of light. Yes, the one that Hugh Everett, David Deutsch, and other physicists interpret to mean that we live in a multiverse. Here, for example, are my photographs of a similar phenomenon, light diffraction. Here the rays of the sun penetrate into the room through one narrow gap between the curtains. There are scientific works that suggest the passage of a photon through 3 or more slits, but the classic one is the double-slit experiment. Let's remember what we're talking about. To demonstrate the interference of light, you can take 2 sheets of paper and fold them in series. Let's make 2 slits in the first sheet and direct a stream of electrons to it. It is best to do this not with a flashlight, but with a laser pointer, or even use natural sunlight. It is expected that two stripes will appear on the second sheet, corresponding to the places where electrons pass through. But in practice, we see a number of vertical stripes characteristic of wave interference. Electrons passing through a double slit exhibit wave properties, as if they were passing through both slits simultaneously. Even when sending electrons one at a time, interference still occurs. This means that one electron somehow passes through both slits at the same time. This is amazing. How can an electron, a single particle, act on itself as if it had passed through two slits at the same time? Moreover, other experiments have shown that electrons can disappear and then appear in other places, which is very strange. If Planck's constant affected objects on a large scale, our world would be incomprehensibly strange, with objects disappearing and reappearing or being in two places at once. Quantum theory, although it seemed confusing and full of paradoxes, quickly showed amazing results. In 1925, Erwin Schrödinger, an Austrian physicist, presented his famous equation that accurately reflects the motion of particle waves. It is so fundamental that the entire periodic table can be explained using this equation. Dirac's electronic theory. At the age of 22, the intrepid young physicist Paul Dirac decided to combine the concepts of space and time by creating a wave equation corresponding to Einstein's special theory of relativity. He created the theory of four-dimensional symmetry, which made it attractive and concise. The complex elements of the Schrödinger equation were replaced by a single four-dimensional equation. The Dirac equation also explained where the magnetic field comes from in magnets without moving charges. It turned out that the electron has a property of rotation called spin. It is the spins of electrons in a metal that create a magnetic field. Dirac's equation opened the door to understanding a new form of matter called antimatter. It is identical to ordinary matter, but has the opposite charge. For example, an anti-electron or positron has a positive charge. It is theoretically possible to create anti-atoms from positrons orbiting antiprotons and antineutrons. For example, people learned to create antihydrogen atoms back in the mid-1990s. But when matter and antimatter come into contact, an explosion occurs, releasing enormous amounts of energy. In the context of universal theory, antimatter is of key importance, since every particle must have an antiparticle. Previously, symmetry was perceived by physicists as a beautiful detail, but not critical for theories. However, they were now surprised by symmetry's ability to predict new and surprising phenomena such as antimatter and electron spin. Physicists realized that symmetry is a fundamental characteristic of the universe. However, there were also questions that remained unanswered. For example, if an electron has wave characteristics, what creates that wave? What exactly is fluctuating? And how can a wave pass through two different holes at the same time? What the hell? Why can't my coffee be in two places at once, but an electron can? The problem that has come into the spotlight has divided all scientists in the world into two camps. In 1926, Max Born argued that the true essence of vibration is the probability of finding an electron in a particular location. Thus, we cannot know with certainty exactly where an electron is located, but we can determine the probability of its presence in a particular place. This approach was a real revelation. He meant that the future cannot be accurately predicted. One can only estimate the likelihood of a particular event. But despite the successes of quantum theory, many criticized it. Einstein noticed that the more efficient quantum theory becomes, the less logical it seems. Discussions about the philosophical aspects of wave theory continue today. Richard Feynman, Nobel Prize winner, remarked, "I think it's safe to say that no one understands quantum mechanics." Clash of the Titans. On one side of this millennium debate stood Einstein, Clash of the Titans, and Schrödinger. On the other side are Niels Bohr and Werner Heisenberg, pioneers of the new quantum concept. The fate of this confrontation was decided at the Sixth Solvay Congress in 1930 in Brussels. It was there that the main debates of the era took place, during which the giants of physics came face to face in the battle for the meaning of reality itself. Paul Ehrenfest described the moment after one of the quarrels. "I will never forget how I saw two rivals leave the university club. Einstein was a majestic figure and walked calmly with a weak, ironic smile, while Bohr, terribly upset, trotted next to him. Einstein actively criticized quantum theory, trying to emphasize its inconsistency. However, Bohr confidently refuted each of his remarks. In response to Einstein's assertion that God does not play dice with the universe, Bohr replied, "Stop telling God what to do." Most historians believe that the winners in this dispute were Bohr, Heisenberg, and other supporters of the new quantum theory. But Einstein was able to identify and show the weaknesses of quantum mechanics, pointing out its unstable philosophical foundations. Many of his arguments are still relevant today, and at the center of many of them is a world-famous cat. Schrödinger's cat. Schrödinger proposed a thought experiment demonstrating the paradoxes of Schrödinger's cat in quantum mechanics. Take the cat and place it in an airtight container along with a piece of uranium. When an elementary particle escapes from the uranium, the Geiger counter is triggered, activating a mechanism that will kill the cat. The question is posed like this: is the cat alive or dead? Since the phenomenon of uranium decay is determined by quantum laws, the state of the cat should be viewed through the prism of quantum mechanics. According to Heisenberg, until the moment the box is opened, the cat is simultaneously in two states, both alive and dead. The two conditions are confused until you look inside the box and determine the cat's actual condition. In other words, the fact of observation somehow mystically determines reality. To Einstein, this approach seemed absurd. He often asked his guests provocative questions, such as, "Does the moon exist only because a mouse looks at it?" Despite all the paradoxes of quantum theory and its incompatibility with the everyday view of the world, it had an undeniable advantage. Just think, the predictions of quantum theory have been confirmed to within 11 decimal places, making it the most accurate theory of all time. And Einstein himself admitted that quantum theory contains truth. In 1929, he even proposed Schrödinger and Heisenberg as candidates for the Nobel Prize in Physics. And yet, almost 100 years later, scientists have not reached a consensus regarding the problem of Schrödinger's cat. Most physicists simply use quantum mechanics as a recipe book that always gives the right answer, and do not pay attention to its subtle and deep philosophical implications. The old Copenhagen interpretation of Niels Bohr, in which observation causes the collapse of its wave function, is quickly losing its relevance because today, with the help of nanotechnology, we can manipulate individual atoms and perform similar experiments. Therefore, the many-worlds interpretation is becoming increasingly popular, in which reality is divided into two parts. In one, the cat remains alive, in the other, dead. Following the advances of quantum theory in the 1930s, physicists decided to tackle a new mystery. Why does the sun shine? Energy of the sun. Since ancient times, the sun has been the subject of worship. The energy of the sun in different cultures occupies a central place in them. The Greeks sang of Helios, who rode across the heavens every day on his brilliant chariot, illuminating the earth. The Aztecs, Egyptians, and ancient Indians also had their own versions of the sun god. Thus, the source of solar energy remained a mystery for a long time. At the dawn of the 19th century, Joseph von Fraunhofer created spectrographs that were unique for his time. Light passing through a prism forms a rainbow on the screen, showing differences in wavelengths, including dark lines. These lines appear due to quantum jumps of electrons that either absorb or release energy. Since each chemical element has its own unique spectral lines, this allows us to determine the composition of a substance. Therefore, spectrographs are actively used. For example, in forensic science to analyze traces. By analyzing the spectral lines of sunlight, scientists have discovered that the sun is mainly composed of hydrogen. After Fraunhofer's work, astronomers, having studied the light of stars, came to the conclusion that these celestial bodies consist of materials inherent to the Earth. This confirmed that the laws of physics apply the same throughout the universe. What is life? What is life? Erwin Schrödinger, one of the creators of quantum mechanics, asked another eternal question. What is life? Schrödinger believed that quantum mechanics could unlock the mystery of the origin of life. For centuries, scientists and philosophers have theorized that there is a special life force that animates matter when something invisible, such as the soul, enters into it. Many adhered to dualism, believing that the physical body and soul coexisted together. However, Schrödinger was convinced that the secret of life must be encoded in a specific molecule, obeying the principles of quantum mechanics. Just as Einstein eliminated the ether from physics, Schrödinger wanted to eliminate the concept of life force from biology. In 1944, he published the book What is Life? In it, he described the principles according to which the code of life is transmitted from generation to generation, not thanks to some ephemeral entity, the soul, but thanks to a special molecule contained in cells. In those years, human knowledge in the field of molecular biology was, well, let's say, fortune-telling on coffee grounds. However, Schrödinger's book inspired James Watson and Francis Crick to search for this key molecule. Realizing that due to its miniature size it was impossible to see with the eyes, they used X-ray crystallography, the wavelength of which corresponds to the size of the molecules. X-rays, passing through crystals of organic substances, were scattered, forming unique patterns. These patterns helped reveal the atomic structure of the crystal. I think it's amazing that quantum mechanics is such an advanced tool that it can be used to determine the positions of atoms and molecules. Like children's construction sets like Lego, you can connect atoms in the right order, recreating the structure of complex molecules. Watson and Crick discovered that DNA is a key component of the cell nucleus. Based on X-ray photographs taken by Rosalind Franklin, they determined that DNA was shaped like a double helix. That is, the structure of DNA was discovered using quantum mechanics. Amazing! This result clearly demonstrated that the process of reproduction can be demonstrated at the molecular level. This breakthrough allowed researchers to begin the truly ambitious Human Genome Project, which aimed to obtain a detailed atomic description of DNA. As Charles Darwin predicted in the 19th century, scientists can now create a family tree of all life on Earth. Nuclear forces. Einstein failed to create a comprehensive field theory, largely due to a lack of information about nuclear forces. There are two types of interaction, strong and weak. Considering that protons have a positive charge and, according to theory, should repel each other, the nucleus of an atom, according to theory, should fly apart into pieces. However, it is the nuclear forces that resist this repulsion and hold the nucleus together. Without these forces, our world would simply collapse, turning into many individual particles. Thanks to the strong nuclear force, the nuclei of many elements can maintain their stability throughout the existence of the universe. But there are nuclei that are unstable due to an excess of protons or neutrons. If there are too many protons, electrical forces can destroy the nucleus. If there are too many neutrons, their internal instability can cause decay. Weak nuclear forces cannot hold a neutron forever, so over time it is destroyed. As a result, three particles are formed: a proton, an electron, and another particle called an antineutrino. In 1929, Ernest Lawrence created the cyclotron, which became the basis of modern particle accelerators. The operation of a cyclotron is based on a simple principle. A magnetic field sets protons in motion along a circular path, where at each revolution they receive an energy impulse from the electric field. After many revolutions, protons can reach energies of up to billions of electron volts. These protons are then targeted and collide with other protons. By analyzing the collisions, scientists were able to detect previously unknown particles. This process can be thought of as trying to determine the properties of a piano by throwing it out of a window and analyzing the sound of the fall. Despite the cumbersome nature of the method, this is one of the few ways available to us to study the internal structure of the proton. When scientists first collided protons at an accelerator in the 1950s, they discovered a variety of unexpected particles. This shocked them, since it was expected that with in-depth analysis, the structure of the nucleus would become simpler, not more complex. These results may lead one to think that nature is acting illogically. Frustrated by the constant emergence of new particles, Robert Oppenheimer proposed that the Nobel Prize in Physics be awarded to the person who did not discover new particles within a year. Enrico Fermi said that if he had imagined the presence of so many particles with Greek names, he would have chosen the profession of a botanist. Physicists were overloaded with information about elementary particles. Because of this problem, some thought that the human mind was fundamentally incapable of understanding the world of subatomic particles. They compared it to how impossible it is to teach a dog to count. However, the situation began to become clearer thanks to the work of Murray Gell-Mann, according to which the proton and neutron must consist of three smaller particles called quarks. In 1964, the omega- particle predicted by his theory was discovered, for which Gell-Mann received the Nobel Prize. The weak force and ghost particles. Scientific research related to the weak nuclear force, which is 1,000,000 times weaker than the strong force, continued to develop rapidly. The weak nuclear force fails to hold the elements of some atomic nuclei together, causing them to break down into simpler components. This mechanism, known as radioactive decay, explains the high temperature inside the Earth and is responsible for volcanic eruptions and earthquakes. To understand the nature of this interaction, scientists hypothesized the existence of a new particle. For example, an unstable neutron eventually decays into a proton and an electron in a process called beta decay. To properly describe this phenomenon, we had to add another particle to the equation, called a neutrino. Neutrinos are called ghost particles instead, because they are able to fly through entire planets and stars without any interaction or absorption. They are capable of moving almost at the speed of light, and their number exceeds all the atoms in the universe. Right now, a stream of neutrinos from deep space, some of which previously passed through our planet, is passing through your body. Why? These particles could fly freely through the thickness of solid lead, stretching from the Earth to the Sun. Wolfgang Pauli, who predicted the existence of neutrinos in 1930, once complained, "I have committed an unpardonable sin. I imagined a particle that cannot be observed." But as elusive as this particle was, it was eventually discovered experimentally in 1956 while analyzing the powerful radiation emitted by a nuclear reactor. In an attempt to better understand the weak nuclear force, scientists have proposed a new principle of symmetry. Since the electron and neutrino are a pair of weakly interacting particles, it has been proposed to combine them. This assumption led to the creation of a new electroweak theory that combined electromagnetism and the weak nuclear force. The electroweak theory, developed by Steven Weinberg, Sheldon Glashow, and Abdus Salam, won them the Nobel Prize in 1979. Instead of combining with gravity, as Einstein had assumed, light combined with the weak nuclear force. Thus, out of many uncertainties, a new concept began to emerge, known as the Standard Model of elementary particles. The theory of almost everything. Interestingly, the Standard Model was able to accurately determine the properties of matter in the past, down to a fraction of a second after the Big Bang. However, despite the detail of the Standard Model and its ability to reflect our understanding of the subatomic world, a number of gaps remain. First of all, it lacks gravity, which is, to put it mildly, a serious drawback, considering that gravity controls the macrostructure of the universe. When scientists try to add gravity to this model, they encounter unsolvable equations, making the model unsuitable for explaining some of the mysteries of the universe, such as events before the Big Bang or the contents of black holes. The Standard Model was created by combining different theories into a puzzle consisting of different parts. As one physicist put it, it's like sticking a platypus, an anteater, and a whale together with duct tape and declaring the result to be nature's most elegant creation. In fact, only a mother could love such a creature. The Standard Model contains many unidentified parameters, such as the mass of quarks and the strength of interactions, 20 constants added artificially, without a clear understanding of their origin and significance. To understand the scale of the problem, let's simply compare Einstein's equation and the Standard Model. Einstein's theory, for example, can be reduced to one short equation, whereas the equations of the Standard Model, in their highly abbreviated form, take up almost an entire page as they list in detail the various quarks, electrons, neutrinos, gluons, Yang-Mills particles, and Higgs particles. All the physical laws of the universe can in principle be derived from this single page of equations. The problem is that the two theories, Einstein's theory of relativity and the Standard Model, are based on different mathematics, different underlying assumptions, and in different fields. The ultimate goal is to combine these two sets of equations into a single final system. Any theory that claims to be the theory of everything must contain both systems of equations, but at the same time remain finite. So far, the only theory that can do this is string theory. String theory, prospects and challenges in the late 19th and early 20th centuries, two key concepts dominated science: Newton's law of gravity and Maxwell's equations for describing light. Einstein recognized that they were incompatible and was sure that one of them would be wrong. The fall of Newtonian mechanics became the starting point of the largest discoveries of the 20th century. Today, history is repeating itself. In science, there are again two competing concepts. On the one hand, there is Einstein's theory of gravity, which talks about black holes, the Big Bang, and the expansion of the universe. On the other is quantum mechanics, which studies the world of particles. However, these theories are incompatible with each other. It is likely that the next breakthrough will connect these two directions. In 1968, two scientists, Gabriel Veneziano and Michio Suzuki, discovered an interesting formula created by mathematician Leonhard Euler in the 18th century. This strange formula seemed to describe the scattering of two elementary particles. But how could an abstract formula from the 18th century describe the results obtained with modern accelerators? This doesn't happen in physics. Soon other scientists, including Yoichiro Nambu, Holger Nielsen, and Leonard Susskind, realized that this formula represented the interaction of two strings. They extended this idea to a whole army of equations describing the scattering of multistrings. They were then able to introduce spinning particles into string theory. String theory became something like an oil well from which a fountain of new equations suddenly appeared. But where do so many different particles come from? The theory stated that each vibration of a string, like a musical note, corresponds to a specific particle. Electrons, quarks, and Yang-Mills particles are simply different harmonies of the same vibrating string. What makes this theory unique is the natural inclusion of gravity. The graviton in it is one of the lowest vibrations of the string. And even if Einstein had never come up with his theory of gravity, we would have found it just by looking at the lowest vibration of the same string. Here's an example. When analyzing the collision of two graviton particles, the result is infinite and therefore meaningless. However, when the two strings collide, the result is two terms that exactly cancel each other out, helping to create the final theory of quantum gravity. 10 dimensions. As the theory developed, such features began to appear that personally, the 10 dimensions gave me goosebumps. In particular, it turned out that she paused 2 seconds with a black screen. Further interstellar music in the background, can only function in 10 dimensions. This came as a real surprise to physicists, since this kind of discovery had never been made before. Generally, theories can be adapted to any number of dimensions. It seems to us that we live in three-dimensional space, moving left and right, up and down, forward and backward. Given time, 4 dimensions are enough to describe any event. For example, to arrange a meeting in Berlin, you just need to indicate the address, gender, and time. Our perception is limited to these 4 dimensions, and it is almost impossible to imagine additional dimensions. That is why the study of multidimensionality in string theory is carried out primarily using mathematics. If the assumptions of string theory are correct, then our universe was originally 10-dimensional. However, such a model of the universe would be unstable, and 6 of the 10 dimensions would eventually collapse, becoming so small that their atoms would be too large to interact. Supersymmetry symmetry in equations has long been considered a good, but not essential, quality. But in quantum physics, symmetry becomes a key element. Michio Kaku writes, "Only in recent decades have physicists realized that symmetry is not just a nice feature of the theory, but rather a central component of it. Requiring that a theory be symmetric can often eliminate the inconsistencies and anomalies inherent in asymmetric theories. Symmetry is the sword with which physicists defeat the dragons unleashed by quantum corrections." Dirac discovered that his equation for the electron indicated the electron's spin, a property similar to the spin we are familiar with in everyday life. Subsequently, it turned out that all elementary particles have a spin, which can be whole or half-integer. Particles with integer spin, such as photons, Yang-Mills particles, and gravitons, are called bosons and carry the fundamental forces of the universe. On the other hand, particles with half-integer spin, including electrons, neutrinos, and quarks, are called fermions. It is fermions that make up protons and neutrons, and therefore the atoms that make up our matter. Then Bunji Sakita and Jean-Louis Gervais showed that there is a new type of symmetry in string theory called supersymmetry. This is the most complete symmetry ever discovered in physics. It unites all known particles. This symmetry allows particles to be replaced by each other in equations without changing the underlying structure. Each particle has its own twin in this symmetry, which is called a superparticle. For example, a pair of electron is a C-electron, and a pair of quark is a squark. Michio Kaku writes, "Something remarkable is happening in string theory. When calculating quantum corrections to string theory, we have 2 components. There are quantum corrections that come from fermions, and others that come from bosons. They are miraculously the same in size, but opposite in sign. One of the terms may be positive, but at the same time there is another term, negative. When added, they cancel each other out, leaving the final result. For a long time, scientists were unable to combine the theory of relativity and quantum physics. However, supersymmetry allows infinities to be neutralized, which makes this unification easier. Einstein once compared his theory of gravity to marble. It was smooth, elegant, and polished. Matter, on the contrary, resembles wood, clumsy, chaotic, and lacking regular geometric structure. Einstein's ultimate goal was to create a unified theory that would unify marble and wood, that is, a theory made entirely of marble. This is exactly what Einstein dreamed of. String theory in this case connects marble bosons and wood fermions. Steven Weinberg, we recall, a Nobel Prize winner, wrote, "Although symmetries are hidden from us, we can feel that they are implicitly present in nature, governing everything around us. This is the most exciting idea I know. Nature is much simpler than it seems. Nothing gives me greater hope that our generation truly holds in our hands the key to the universe, that in our lifetime we will be able to say why everything we see in this vast universe of galaxies and particles is logically inevitable." If you sum up everything said in this video, It turns out that symmetry is very similar to the key to unifying all the laws of the universe. Let's just list. Symmetry brings order to chaos, forming ordered systems of chemical elements and particles, helps identify missing links in theories, predicting new elements or particles, finds connections between objects that appear to be independent between space and time, matter and energy, electricity and magnetism, fermions and bosons, leads to the discovery of new phenomena such as antimatter, spin, and quarks, eliminates unwanted effects that can destroy the theory, quantum corrections with divergences and anomalies are eliminated using symmetry, changes the original classical theory, quantum corrections to string theory change the original theory, defining the dimension of space-time. It is believed that at the beginning of the universe there was a single superinteraction, the symmetry of which covered all particles. However, this symmetry began to break. First gravity emerged, then nuclear forces, leaving electromagnetic forces on their own. Thus, the current world seems fragmented, where every interaction is different from the previous one. The task of physicists is to reunite these broken parts. M-theory superstring theory has the potential needs of M-theory, but there is a problem. This cannot be expressed in one equation. In 1995, an important event occurred that led to the emergence of M-theory. The crux of the problem was that there were 5 varieties of string theory, differing only in the way the spins were organized. This has raised questions because most scientists believe that the universe must be unique. Physicist Edward Witten discovered that there is a hidden 11-dimensional theory called M-theory. It is based on membranes similar to the surfaces of spheres and donuts. Witten argued that 5 different string theories could be interpreted as 5 ways of transforming an 11-dimensional membrane into a 10-dimensional string. In other words, all these versions of string theory are different mathematical models of the same M-theory. It follows that string theory and M-theory are different projections of the same idea. But how can one 11-dimensional concept give birth to 5 10-dimensional ones? Imagine a beach ball. If you let out almost all the air, it will take the shape of a sausage. If you blow it off completely, you get a string. Essentially, the string is a disguised membrane from which air is released. Starting with an 11-dimensional ball, one can mathematically prove that there are 5 ways to deflate it into a 10-dimensional string. Or remember the parable of the blind men who met an elephant for the first time. One, after feeling his ear, decided that the elephant looked like a fan. The second, having become acquainted with the tail, decided that the elephant looked like a rope. A third, who examined the leg, suggested that the elephant looked like a cylinder. But in fact, when we look at the elephant as a whole, we see him as a voluminous, ponderous, handsome man with kind eyes and velvet ears. Likewise, the 5 string theories are associated with different parts of the elephant, but the true nature of M-theory, the elephant, is yet to be revealed. Holographic universe just 2 years after introducing M-theory in 1995, Juan Meldacena made a phenomenal discovery. His research showed that supersymmetric Yang-Mills theory, operating in 4 dimensions, is mathematically equivalent to 10-dimensional string theory. This caused quite a stir in the physics world, and by 2015 the discovery had been cited in 10,000 papers, making Meldacena's work the most influential in high-energy physics. At the beginning of the video, we discussed the duality of Maxwell's equations between electric and magnetic fields. These equations retain their form if these fields are swapped. Likewise, there are 5 10-dimensional string theories that are dual to each other because they all combine into a single 11-dimensional M-theory. That is, duality suggests that both theories are different sides of the same phenomenon. However, Meldacena proved that there was an additional duality between 10-dimensional strings and 4-dimensional Yang-Mills theory. This discovery came as a surprise, indicating deep connections between gravitational and nuclear interactions in different spatial dimensions. Michio Kaku writes, Usually duality is found between strings of the same dimension. For example, by rearranging the terms that describe these strings, we can often replace one string theory with another. This creates a whole web of dualities between different string theories that are defined in the same dimension. But the duality between two objects defined in different dimensions was an unheard of event. The question raised by this duality is not just an academic speculation. This has implications for our understanding of nuclear interaction. For example, we already know that the best way to describe it is a four-dimensional gauge theory based on the Yang-Mills field. However, no one has yet been able to find an exact solution to this theory. Given that gauge theory can be related to 10-dimensional string theory, this points to a possible interconnected understanding of quantum gravity and nuclear force. This idea brought attention to the fact that basic properties of nuclear forces, such as the mass of the proton, can best be explained using string theory. This caused a real identity crisis among physicists. Nuclear physicists, who had traditionally studied three-dimensional objects, were suddenly faced with the need to study string theory in 10 dimensions. This raised questions about the connection between gravity and gauge theory. In addition, an interesting principle was discovered, called holographic. A hologram is a two-dimensional image that can reproduce a three-dimensional image using a laser beam. This is how our 2D2 from Star Wars projects the image of Princess Leia, and this is how haunted houses at Disneyland are created, where 3D ghosts glide around you. Similarly, in black holes, all information about the objects inside can be encoded on the two-dimensional surface of the event horizon. If you throw the Bible into a black hole, then according to quantum mechanics, the information contained in the book cannot disappear. So where does this go? It is probably distributed over the surface of the event horizon. So, the two-dimensional surface of a black hole contains complete information about all three-dimensional objects that fall inside. This discovery challenges our understanding of reality. We think of ourselves as three-dimensional beings, but perhaps we are actually part of a hologram. Michio Kaku writes, "Perhaps the three-dimensional world we perceive is just a shadow of the real world, which is actually 10 or 11-dimensional. Moving in three spatial dimensions, we thus perceive the movement of our real self in 10 or 11 dimensions. When we walk down the street, our shadow follows us and moves just like us, except that it exists in 2 dimensions. In the same way, we ourselves may imagine shadows moving in 3 dimensions, but our real self moves in 10 or 11 dimensions." It turns out that string theory continues to offer increasingly surprising conclusions today. This indicates that we still poorly understand the foundations on which it is built. For this reason, experimental testing of string theory seems premature. Once we discover its true principles, we can find a way to test it experimentally. Then we will be able to say for sure whether string theory is a theory of everything or a theory of nothing. Thank you for watching. Subscribe to the channel to receive notifications about new videos, and don't forget to like and comment.